Hi everyone, my name is Sergei Weber. I have the pleasure to host the next session. Next, we're pleased to welcome Janos Kovacs, Yanni, working as a cyber risk analyst at Cymotive and as a visitor professor at the University of Obuda. Janos named his presentation, and there's a pun intended, tough as steel, a practical example for applying targeted attack feasibility in an ECU project. In his talk, Janos will shed light on the tough concept from the ISO PAS 8475. He will explain how this concept provides a harmonized approach to managing cybersecurity risk, especially when dealing with unique security challenges or even legacy architectures. So let's give a warm welcome to Janos. Janos, the stage is yours.
Thank you. Hi, everyone. First, let me share my screen and start the presentation. Okay, I think you are hopefully all seeing my screen now. Cool, thanks for the feedbacks. So, hi everyone, my name is Janos Kovacs and I'm really proud to be a presenter here speaking about the tough concept which will make the ECUs tough as steel. And I will provide an example which should be some practical guidance for anyone who might willing to apply this tough concept in the future during the vehicle cybersecurity projects. Let me introduce myself shortly. So I am proud to be a husband of a wonderful woman, and I'm the father of two beautiful and bright daughters who making the life of kindergarten teachers harder at the moment, hopefully. I'm also a cybersecurity enthusiast for the automotive industry since more than a decade now. I work as a risk analyst and cybersecurity consultant for Cymotive. Also, I am so lucky to be a visitor professor at Obuda University, my former university. I'm a member of ASRG Vulnerability Management Technical Committee and the creator of the Dimitri project. For that, I attached the QR code. It's an educational game about automotive cybersecurity. And here is our company, Cymotive. We are proud to be the selected cybersecurity partner of Volkswagen Group. We were founded at 2016 by the leaders of the Israeli National Security Services. We are really proud to be able to be among the few companies who are able to provide an end-to-end cybersecurity services for the whole automotive cybersecurity life cycle. And we have provided. I hope I'm audible at the moment. So first, I'm going to speak about the ISO publicly available specification 8475 key takeaways. That will be just in a nutshell to catch up the rhythm. Then I will introduce the targeted attack feasibility concept. After it, I'm going to present some example theoretical ECU project, again, theoretical engine control module with a very rough risk analysis that will be served as our practical examples. And then I will explain the application of the targeted attack feasibility for this engine control module project. Then, hopefully, you will have a lot of questions and I will be excited to answer them. So, what's ISO publicly available specification 8475 is all about? It has two pillars. The first is the cybersecurity assurance level, which is, I must say, a very sought after elaboration of this concept, often mentioned by the ISO 21434. And the pillar is the targeted attack feasibility, which is quite new, but rather handful or handy concept that they introduced. So, as you might all know, at the moment, the cybersecurity assurance level is for specification of the necessary for the implementation, the design, and the testing of the cybersecurity product, the automotive product in the cybersecurity lifecycle. And it starts with the decision of the cybersecurity assurance level, the determination of the cybersecurity assurance level, and the how to use them. So it provides criteria for the design, the modeling, and the coding guidelines. What are the necessary steps to carry out for each cybersecurity assurance level? Then it provides a criteria for the design and the integration. And finally, it provides the criteria for the testing. What are the metrics to be done? What are the metrics needs to be reached? What are the test types necessary? And what are the test cases that are required to be carried out for the automotive cybersecurity project? The next, our topic today, is the targeted attack feasibility, which provides a common language for the cybersecurity specifications for the cybersecurity standards. It all starts also with the decision. Do we need to use the targeted attack feasibility? Hence, we decide here to use it. Then we continue with the determination of the targeted attack feasibility level for each cybersecurity attack path, let's just say so. And then how we shall use the targeted attack feasibility. Then the ISO publicly available specification 8475 describes the TAF concept and its role in the distributed value chain, then the method of the TAF rating, and also it provides some supportive examples for the application of the TAF. So, what is the targeted attack feasibility? The targeted attack feasibility, in a nutshell, is the expected attack feasibility when a cybersecurity control is applied. So it means that if I manage to apply a cybersecurity control, it shall reach a certain level of decrease in the feasibility of the attack. Where it should be used? It should be used in the customer-supplier communication, which is a really, really interesting and useful feature, because we in the automotive domain all exist in a very complex supply chain ecosystem, when this supply chain related issues shall be addressed carefully and with care. Also, it is really important or can be really handy if some cybersecurity controls are omitted or changed compared to a set of cybersecurity baselines, because, for example, different technology is used or legacy hardware is used. So here we can also specify that what shall be the residual feasibility that will satisfy the risk appetite of our organization. And then the how the targeted attack feasibility should be used. The key concept is here to specify the strength of the complementary controls. So if we are not able to use the cybersecurity control in a set of baseline or a set of specification, but we need to use different ones, then we can specify what shall be their effectiveness, I shall say. How does it look like? Here are some examples from the ISO publicly available specification 8475. And here we can see when some vendor, out an example, clearly from theoretical perspective, specify that what shall be the required attack feasibilities for the different attack vectors. For example, if an attack vector is reachable from the open network, then the high feasibilities that would be anyway rated as high, then the network related attack vector's feasibility should be reduced to a medium level. If there is an attack vector that is adjacent, like a Wi-Fi, for example, that should be decreased to a medium level. If there is a local accessibility, then every attack that is otherwise would be rated as medium should be decreased to a low. And with the physical attack vectors, that should be otherwise be a high feasibility rating, that would be needed to decrease to very low. This is just a theoretical example, but I think here you can get the idea. And what is network meaning, or what is adjacent meaning, or what is high, medium, very low meaning? This comes from the ISO 21434-2021, when all of it are elaborated quite well. In other words, just to put thing into movement, let's see how can it looks in the real life. Here is a theoretical threat analysis. In this threat analysis, you can see that here we have the assets of the functional coding and the usage history of some target environment. The functional coding has applicable threats to the violation of integrity or authenticity, like someone tampering the functional coding, causing any adverse behavior of the target environment. And there is the user history or usage history. If someone would get the read access, that could cause the violation of the privacy. Here we have also some attack path. So for the functional coding, it is accessible via the diagnostics and the JTAG interface, and the usage history is available via some IP service or SPI interface. So we also identified that what are the damage scenarios, like I already told you, the adverse behavior of the target environment, or the unauthorized access to any private information. And also here we can see the feasibility if no cybersecurity control is applied, and the impact if no cybersecurity control is applied. The risk is determined, and we see that, for example, if we cannot accept any risk from the medium level, then we shall mitigate the medium and the high risk in this table. So we define cybersecurity goals. I just intentionally not go into the details at what are the cybersecurity goals here, because this is not the key takeaway. But the key takeaway is that the residual feasibility resulting from the cybersecurity goals becomes low and very low. So the cybersecurity goals reached a decrease in the feasibility of the attack. And you can see that here is where the targeted attack feasibility comes into the picture. So if we live in a world when we cannot say that what are the cybersecurity controls that our suppliers, for example, should exactly do, because there are some constraints, then we can say that the residual feasibility can be the specification itself. So we should not say that you should do secure boot, you should do this or secure update or secure diagnostics in a very discrete way, but we can say that the target for your cybersecurity controls should be to reach this feasibility for the attacks. This is the targeted attack feasibility in practice on the move. What are the use cases for the targeted attack feasibility? I see three major ones. The first is the legacy architectures. As the UNEC Regulation 155 is mandatory in certain regions from 2024, even for the vehicle types that has type approval prior, then we might encounter situations when we need to secure legacy architectures that has, for example, hardware constraints, like no additional execution space for additional software content, or there is no proper memory for additional software content, or there are a lack of hardware resources for example, having a hardware security module inside the ECU. Then we can also have the second use case when there is a difference in the technical solutions between the uh, OEM or the customer and the supplier. For example, between a tier 1 and between a tier 2 or between an OEM and a tier 1. So there is the cybersecurity specification of the OEM saying that secure boot should be implemented this and this and this manner. And there is the tier 1 who has the ability to provide a secure boot solution that is slightly different from the one specified by the OEM, but still considered to be robust. Then the targeted attack feasibility can be called to further usage. As I say, okay, I don't do exactly the cybersecurity control you specified, but according to our understanding, the cybersecurity control we use still have the necessary result. Hence, your cybersecurity risk will be mitigated with no actual overhead for the development costs. That's also something we need to take care. And there is also one third use case when we can say that there are different technologies that are overlooked or not covered by the customer cybersecurity requirement. For example, there is a network protocol used that is not covered by the generic specifications. This way, this needs to be secured by the supplier, but common language needs to be found for the communication of the cybersecurity risk between the customer and the supplier. So this is, I think, the key takeaway. This common language, the harmonization of how we see the risks, despite we have different solutions for risk analysis, despite we have different solutions for security controls, but still we are able to understand each other using the TAF concept. Okay, I promise you to present some example, and this example will be a legacy engine control module project, which will be still tough as the steel from the cyber risk. So let's rev up the engines. Also, if we need to rev up the engines after 2024, but we need to do it in a secure way because of the UNEC regulations. So here we have this example and purely theoretical ECU project, which is an engine control module from 2018. So it was developed in 2018, and cybersecurity was not a core part, let's just say so, for the development. I think most of us who ever worked in the cybersecurity supply chain encountered such an issue. But now, we imagine ourselves in today or even 2 years before, the customer approach does that they need to have certain cybersecurity controls in this engine control module, and we need to implement them. The problem is that this is, like I told you, a legacy project. This legacy project used a microcontroller which is really robust, but has few capabilities for cybersecurity control implementation. Let's just put it this very diplomatic way. And this way, we need to solve the cybersecurity requirements with this kind of legacy architecture. During our risk analysis, we identified the following four major attack surfaces, attack paths. The first is the debug interface, of course, very classical one. Via the debug interface, you can get read or write access on the register level, even for the microcontroller, which is bad for the health. And there is also the vehicle CAN data. We exchange data with the CAN bus participants, and this exchange can be a source of harm, let's just say so. And also there is two additional classical ones, the software update, which could be used to introduce a malware or take down the functioning of the engine control module, the diagnostic interface, which could be used for the modification, for example, of the behavior of the engine control module, which is, by the way, sometimes done with the tuning community as well, but that's also not something that is very in line with the cybersecurity policy of our company. We got the following specifications for the customer. They shall have the interface hardening. This interface hardening shall contain the restriction of the debug interfaces, for example, or in this case, the JTAG. The second pillar is the ECU data protection, which should be done by securing the boot process with a very exact specification of some kind of secure boot. The secure UDS, which is quite less flexible, as we as a supplier needs to create an ECU that is compatible with the maintenance infrastructure and ecosystem of the customer. So the UDS needs to behave like it's described, but still might have some trouble in the implementation with this legacy hardware. And also we have the secure software update, which is based on the digital signature checking of the software images signed by the customer OEM. We also have a third pillar, the hardware security, which contain one big chapter about the hardware security module and the requirements toward the hardware security module. And after the analysis, we found that with the restricted debug interface, we are completely good to go, because we have the ability to create an ECU unique access key for the JTAG. Hence, we are able to meet with the customer requirements. The cloud is not so shiny with the secure boot, on the other hand, as the secure boot requires the HSM to communicate with the application or the bootloader, giving the permission for the execution of the images, and or the for example, for the application software, so the software entities. And this is kind of a paradox here, because without the HSM, the enabling entity should be the same, which it should be protected. So this is something that we deem as not feasible. The secure UDS and the secure software update can be feasible, and the separation of duties is feasible inside the ECU, but not in a hardware way. So we need to do some complementary controls, but in general, we are going to be okay. And with the hardware security module, it's completely out of the scope if we want to use this microcontroller. We decide to approach the customer saying that we are okay with the restricted debug interface, and we do the secure UDS and the secure software update by using a one-time programmable memory that will store the certificate used for the digital signature check of the diagnostic requests and for the software update, but we plan to reject the secure boot and the HSM. But life is not so easy, because we just cannot say that, hey, it's legacy architecture, we cannot do this. We need to provide something based on the cybersecurity risk, because the cybersecurity lifecycle of the automotive product should be risk-based as always. Then we turn our faces towards the TARA again, because the TARA here can be the argument for any tailoring, and the usage of the targeted feasibility is very, very easily illustratable with this example. So what would we do if there was no technical obstacle? Here we see that we have two assets in this example TARA, the functional coding again, and the firmware binary. According to our understanding, we are able to violate, or the attackers are able to violate the integrity or the authenticity of the functional coding via the diagnostics and the JTAG. Because this way they are able to override, for example, the tuning, they are able to turn down the engine, or give the engine additional capabilities, additional horsepower, or something like this. And the initial feasibility is medium and low for the diagnostics and the JTAG. The risk we just saw is medium and low. For the firmware binary, we identify that the violation of authenticity is also in the scope, and we can use the software update and the JTAG interface for the violation of the authenticity for the firmware binary. This can be like some form of malware. This malware can cause catastrophic consequences. So these catastrophic consequences should be avoided, and this is also highlighted by the risk analysis with a high and a medium rated initial risk without the application of any cybersecurity safeguards. The cybersecurity goals, if we would be able to follow the customer specifications without any tailoring, would be the secure diagnostics and the secure JTAG for the JTAG and the diagnostics interface. Okay, the risk is low with the JTAG attack surface for the functional coding, but still we are capable of managing this, so we allocate this safeguard there. And then for the firmware binary, we need to apply the secure diagnostics, the secure software update, and the secure boot for preventing the firmware binary from tampering via the software update. And we need to implement the secure JTAG and the secure boot if we want to protect the firmware binary from tampering via the JTAG interface. As I told you, some of the safeguards are not even feasible, and some of the safeguards needs some further tailoring if we want to reach the security risk decrease with the given hardware. So we just go and follow for the residual feasibility. And we can see that the residual feasibility shall be at least low for the functional coding related threats via the diagnostics and the JTAG. And the residual feasibility shall be very low for the firmware binary related threats using the software update and the JTAG. This is the targeted attack feasibility in our case. So using this, we can start thinking about how can we achieve reaching this and how shall we communicate the tailoring for the customer. And we have the updated Tara here with our tailored solutions. Here we can say that the secure diagnostics can be implemented, but with this tailoring using a one-time programmable memory slot for the diagnostic access key or the diagnostic certificate. And this is also protected with the JTAG, that this one-time programmable memory is once written, then theoretically it can be only overwritten using the JTAG. So the secure JTAG outrules or decreases the feasibility of that for a very good security level. Then we have the secure diagnostics, which is also, like I told you, decreased with the same method, and also the secure software update is also using the one-time programmable memory that we created to have the signing certificate stored in a secure way. Because if we close the JTAG and the one-time programmable memory is programmed on the assembly line, then the feasibility of the attack is very low as we intended. This is how we achieve the security risk reduction as desired. We are capable of communicating the tailorings we made, and we are capable of communicating this with the customer in a way both of us will understand and able to store as an appropriate evidence for the cybersecurity management system. So as we see, the targeted attack feasibility can be used for legacy architectures, for any difference between the customer specifications and our technology stack, and for any proprietary or special technologies that are not covered by the customer specifications, or even with situations when the customer doesn't even have any kind of cybersecurity specifications readily made for our consumption. I provided all of this using a legacy architecture engine control module, and we demonstrated that the targeted attack feasibility still can be used as a very handy tool for us in the customer-supplier communication about the cybersecurity risk. Thank you for your attention, and I'm waiting for your questions.
Thanks, Yanni, for the insightful presentation. And thanks for all the hands clapping. I will follow as well. We have a couple of questions. Let me refresh them and ask the very first question. I will show it on stage. So, and it's actually a question from me. Can you elaborate what is the connection between TAF and the given attack feasibility approaches, which we have at the moment in the 2144? Will they replace something or will they enhance?
The TAF uses the same terminology as the feasibility of the risk analysis is required by the ISO 21434. So if I speak about targeted attack feasibility of low or very low or medium or high, this equals with the same as the ISO 21434 attack feasibility, whether it's CVSS based or an attack vector based or an attack potential based one. So if I say that you use CVSS based or let's just say CVSS based attack feasibility approach, and you reach until a level that say the attack feasibility should be decreased at least to low to reach the acceptable cybersecurity risk, then it can be without any change transferred to targeted attack feasibility.
Mhm. Thank you very much. Then the next question is from Sebastian. Here we go. Do you see TAF more as a wish, not knowing options yet, or as a fact, considering known options?
This is an available solution. Just as cybersecurity assurance level, this is not a requirement, not a hardwired requirement of the ISO. So this is why ISO public available specification stands for. So it is specified. All of the guidance, hopefully, I hope at least this moment is provided for its usage, but it's not required. It's a tool. It's an equipment for you to make your life easier by the harmonization of the terminology.
Then we have a question from Kati. How could integrating TAF into cybersecurity risk assessment process help improve the accuracy of vulnerability detection and exploitability evaluation under 2144?
I think that that the targeted attack feasibility is not for this purpose, because if we detect a vulnerability, that is the area of the operations, and of course after the analysis, the targeted attack feasibility can come to the picture, because then we need to evaluate the exploitability, and in this exploitability we get for a certain feasibility for the attack. And if we have an already specified targeted attack feasibility for that attack surface, and this feasibility, or let's just call exploitability, outreaches this targeted attack feasibility, then we need to implement security controls and start the mitigation.
Understand. Then we have a question from Anil. Can a similar method be feasible for impact rating, can we target to decrease impact rating via additional controllability according to functional safety and keep attack feasibility the same? Do you think if it may work?
Question. Thank you. I think it's a really good idea, and I think it can be done. But it's just a possibility. So the current paper I processed for this presentation doesn't deal with this. But the effect of a cybersecurity control should be always either the decrease of the feasibility or the decrease of the impact. So as much as we were able to elaborate this idea with the and reach the goals with the reduction of the feasibility, we can also reduce the impact. For example, by, I don't know, proper user awareness, the impact of the privacy-related issues can be decreased, or by the proper set of security principles, like keeping the least privilege for the applications, the impact of the successful attack can be decreased. There is some partition that doesn't reach the safety partitions in the system, will result in the decrease of the safety impact of a risk. But this is just a matter of discussion and a matter of communication between the customer and supplier. So I think it's definitely feasible and livable option to decrease the impact.
So you based your presentation on a specific information from the working group, I guess. And there's a fitting question from Rafal. Do you know what is the latest status of the 8475 you presented? I think I heard that it is the draft state now and going to be released at the end of this year. Do you have any more up-to-date news about that?
Unfortunately, I'm not able to serve with additional news. I hope this release will happen at the end of the year, and I'm really positive that this will be a huge leap for enhancing the supply chain security issues in the automotive industry.
Good. Then maybe one last question. Let me just briefly skim through it. Here, maybe this one. The latest question from Varish. What is your opinion on moving to a risk acceptance level based approach, whether the goal is to reduce the overall risk to acceptable level? In this way, you can also include not only the feasibility, but also impact level.
Yes, I think the overall goal is to reach the risk to an acceptable level. This was my main approach in the presentation and the practical example as well. So if you remember, my focus is not on the feasibility, but on the risk itself. If I needed to reduce feasibility, all it was because I needed to reduce the risk. The targeted attack feasibility was not about the reduction of the risk overall, but it is an argument for us for using a different solution to reach exactly the same risk reduction, because we have a security control that has impact on the feasibility. So I think, yes, it's all about the risk acceptance level. It's all about that. The targeted attack feasibility is for the harmonized communication of the effect of the cybersecurity controls.
Thank you, Yanni. Great insights. Let's see, or let's meet again in the lobby. So all of you who want to mingle, to get in touch with Yanni and to ask more questions, more technical questions. So please follow Yanni to the lounge. All the others, we meet again in 5 minutes for the next session from Lionel, exploiting EV charging networks, pathways to potential blackouts. So stay tuned. In 5 minutes, we proceed. Thanks, everyone.
Thank you very much for your attention, and I wish you a great day and have fun on the upcoming presentation.